Where's the screen share button? They keep moving things. Or did they move the screen share button? Give me 1 second.
Oh, on the bottom.
Bottom.
Yeah, I have a lot more icons than the participants do. I got like 12. So it was like
Oh,
they got shuffled around.
okay. They expect you to be more ahead of all the rest.
I have 5 different meeting apps that I use between work and school. So it's always like, okay, where did this button go for this app that I'm using right now? Those sorts of things.
Okay.
Okay. So welcome to the October meeting for the Tucson Amateur Astronomy Fundamentals Special Interest Group. I'm Connor Justice. I'm the leader of the group. I will be one of the speakers tonight as well. The other speaker tonight who was talking about Mars, Stephen, if you wanted to go ahead and introduce yourself.
I'm Stephen. I'm been in the group for quite a few years now, and I'm going to be delivering well, I'm not sure if it's a short presentation, but it'll be a presentation on Mars and how to observe it in just a few minutes.
Yay.
So with that, in order to save on time, we're just going to go ahead and get started. So the constellation for this month is Aries. And when I initially sent out the notice for this, I was hoping the constellation would actually have a bit more stuff to it. Unfortunately, it's a fall constellation, and like a lot of fall constellations, there's not a lot of stuff of interest within them, with the exception of like a couple. So this will probably be a fairly quick presentation overall. So Aries is a mid-sized constellation, about 39th in size of the 88 currently modern constellations, making it, and it is also slightly larger than Capricorn. It is one of the original constellations that was cataloged by Ptolemy in the 2nd century. It has Babylonian in origin, like many of the zodiac constellations, including Virgo, Scorpio, Libra. All of those originally hail from Babylonian mythology. It, like all zodiac constellations, crosses the plane of the ecliptic, which is the imaginary disk that almost all objects in our solar system reside on.
I can't get it to let me do anything. It keeps non-responding and killing itself.
Sorry, I thought someone was having a question, so I took a pause. It, as I kind of mentioned, it contains no Messier objects, Caldwell objects, open clusters, or globular clusters. So this constellation is pretty barren. I'm getting a notice that my internet connection is unstable, so if I start breaking up, please let me know. And kind of one of the things that we'll talk here, sorry, jumping ahead of myself. Conveniently, it is also the radiant point for a couple of meteor showers this October. One of them, I think it's the autumn Arteriids, peaks tomorrow, but these are pretty light meteor showers compared to some of the major ones like you would get like with the Taurids or the Orionids or the Leonids or the Perseids. So I'm not quite sure what sort of fall rate you can expect for these 2 meteor showers, but there are a couple of meteor showers this month that originate from within Aries. So keep your eyes out. Maybe you'll see 1 or 2. So being a Greek constellation, it is actually one of many constellations that has a decent amount of lore behind it. We'll focus on one of the 2 stories that are most prominent with it. Aries is considered the chieftain of the zodiac, or the head animal of the zodiac, because its position in the sky puts it in a very unique position. Was the origin point for sunrise during the spring equinox, which in ancient times was the beginning of a new calendar year. So it was also tied to the god, the Egyptian god Amun-Ra, who was depicted as a man with a ram's head. So you still get this relationship between the ram and the sun across multiple different cultures. The ram is also considered to be the origin of the golden fleece that was taken by Jason and the Argonauts in that particular famous story. And one of the other myths involving Ares is that he assisted with the creation of the Hellespont, which is a channel that separates Europe from Turkey. And by assisted, really, he let one of his passengers fall to their death, and the impact made a giant crack in the earth, which became the Hellespont. So not much over there. Its most noticeable appearance was in the Tale of the Odyssey, that was cataloged by Homer. In one of the adventures of Odysseus and his men, they found themselves on the island of the Cyclops, prey to the giant one-eyed monster. And their plan was they needed to trick the Cyclops into letting them go because he had blocked off their only route of escape from his cave nest with a giant boulder. Like a lot of things in Greek culture, they basically drug him, which is probably how they managed to catalog all the other constellations with so many drugs lying around. I also don't know where you would find drugs in a cave of a Cyclops, so that's kind of always like, huh. And during the Cyclops' blind rampage, drug state, they blinded him by stabbing him with a giant tree that they had burned in a fire. The remaining men that hadn't who had managed to escape the Cyclops' ravenous hunger, escaped by tying themselves to the underside of the Cyclops' flock of sheep that he was overseeing, and the Cyclops, thinking of this, would periodically check the sheep to make sure that they weren't trying to escape, but he, for some reason, just didn't check thoroughly, and they were still able to get out. In this case, the sheep is commonly referred to as being symbolized by Ares in this particular case. Any questions so far? Okay. This is an ancient star chart for Ares in the night sky. You can see it's actually, I'm not quite sure what the fly represents anymore. In terms of constellation, this is probably one that was has since been deleted from star charts. But you'll also notice over here that it's actually pretty close to the Pleiades. Let me see something here. There we go. Laser pointer. There we go. It's over here. The Pleiades are back to the left of Aries. So if you could find Taurus, which is over here on the left, down underneath it we have Cetus, and then to the right we have the Pisces, the fish, and above it Triangulum. So that kind of gives those familiar with some of these constellations. It gives you an idea of where they are in the night sky, especially because Taurus and the Pleiades are becoming more prominent. So it gives you some pretty easy landmarks to go and find out kind of where Aries is in the night sky. Let me turn that off. As I said, it is a fall constellation, so it is typically in the skies from September to late March. It's found, as I said, underneath between Triangulum, Cetus, and the Pleiades. And it is well visible within the skies from our latitudes, being a northern constellation. Another star chart kind of giving an alternative view of where it is. Again, laser pointer. Again, down here is Cetus, Pisces. So curious while I was making these, do you also note that Uranus is actually within Aries right now? And I think Mars, someone correct me, Mars is also moving into Aries, if I am not mistaken. Anyone comment on that? Correct me if I'm wrong. Oh, okay. So here within a couple of months, we'll probably see them both within the same region of sky. Does anyone know if there's a chance that Mars is going to be within or near the Pleiades here in a couple of months? That would make for some interesting photography. No?
I don't think it moves that fast.
Well, I mean, in April, it was over by like Mars and Jupiter. Now, like 5 months later. So this isn't that much farther. So I think like what, December or January, it might be over here.
Well, it's going to appear to be going retrograde yet for a while because it's just coming up on opposition. So.
Okay. Definitely something to keep your eyes out for, though. And kind of another star chart showing, instead this time of its position, more about some of the objects you might see, which you can see not a lot. Mostly some faint stars, magnitude 4 or dimmer, 2 or magnitude 2 or higher. It's a quick chart summary of some of the objects we'll see. Plenty of galaxies. Unfortunately, a lot of these are within magnitude 11 or 12 or higher, making them fairly difficult observation targets unless you're underneath very dark skies like at CAC. And even then, some of these would probably be very small that you would need a relatively high-powered telescope in order to resolve any details about them. As we'll see here in a second with NGC 972, it's just kind of a small fuzzy blob. So we'll talk for objects in the catalog in Aries. I will be doing 2 stars and 2 deep sky objects, and that'll kind of wrap up the presentation. So starting off, we have Hamal, Alpha, or the Alpha star of Aries. It is the brightest star in the constellation, following its Bayer designation. It is extremely close for stars as far as ones that we've given in constellations in months in the past, being only 68 light years away, which is, you know, in the suburbs compared to some of the other stars that we might talk about, like Deneb, which is over 1,000 light years away, I think. Or typically we see stars that are in like 200 to 600 light years, so really close. It's magnitude 2. And it is 1.5 solar masses, and it has a luminosity of almost 100 times that of our own sun. It forms the head of the ram, which, if I go back, I'm not quite sure how you get a ram from this. I mean, I guess you can kind of see it like here's the neck, and then the head's like around here, and then these are the horns. But kind of hard. Go back this way. It is a red giant of the K2 spectral class. So it is more into the reddish range compared to our sun, which is a yellow dwarf, which is I think a G9. And we know it has at least one planet roughly the size of Jupiter orbiting it, and it is also used as a standard candle star for the measurement of the stellar classification of other stars. So what this is trying to say is that when professional astronomers are trying to catalog other stars, they are using Hamal as a reference star to help determine the spectral class of other stars. So this is like Vega, which is used as a reference star for the apparent magnitude scale. This is a reference star for determining stellar classifications, which I thought was actually really interesting. Kind of giving you its position, as we kind of pointed out. Oh, hey. There's Eris. We'll talk about that in a second. Pointing out, it's kind of here in the middle of the constellation. I think it's the brightest star within this region of space. You know, where between like Taurid and Pleiades and Seed, between the Taurus, Triangulum, and Pisces. So it should be at least a good reference point. Also, conveniently, this was taken here last night, so this should be accurate. But Aries, the planetoid Eris, and Mars are actually fairly close to each other right now. So something to keep your eyes out for. And over here we have an HR diagram kind of showcasing where the star fits in the overall stellar evolution. And it's, as we had said, it's in the red giant phase, so putting it right up here towards in the mass range of red giants, almost a super giant, which is kind of up to the top more. After Hamal, we have Sheraton, which is the second brightest star in the constellation. It is also extremely close to Earth at a distance of about 60 light years. It's a little bit dimmer than Hamal at a magnitude 6.6. And its luminosity is about 25 times that of our sun, and its mass is about 2.5 times that of the sun. It fits in the position of the horns of the Ram asterism, and it is a spectroscopic binary. So the two stars in the binary are actually orbiting so close together that we haven't been able to resolve them yet with professional equipment. We only know that there's a binary there from doing spectroscopy on the star itself. But we haven't been able to actually resolve the two individual stars visually. Sheraton is a main sequence star fitting in spectral class A5. And we don't actually know what the companion star is classified yet. I think there, from what I was seeing, there's some guesses that it's an F3 or somewhere in the F range class of stars, but it hasn't been officially determined yet. Again, so more up here towards the, I don't know, the front, closer to Pisces, excuse me, over on the constellation, and fitting over way more. So for those who aren't familiar, the sun, I think, fits kind of right down here in the HR diagram. It's kind of on the low end. So Sheraton is kind of way up this chain in the main sequence line. On to two deep sky objects. We have this one, NGC 772. It is a face-on spiral galaxy, about 130 million light years away. It is tidally interacting with a couple of dwarf galaxies that are in orbit around it, which has led it to have this irregular spiral tail that's longer than the others. It's fairly, I think I miscopied my apparent size measurements from another presentation because I usually see the face. I'm not quite sure this argument. I think this should be 18. Otherwise, this picture would be very small. So this is kind of a rough scaling of what you might expect. So this was done on an 8-inch Schmidt Cassegrain with a 10mm eyepiece. So you should probably definitely be able to make out the core of this galaxy and maybe a little bit of the spiral arm, even underneath good skies that you would get over at Tempa. You probably won't see much of the outer portion of the spirals, which are kind of these fainter, lighter areas, without probably something more like a 10-inch or higher telescope. Kind of its rough position within the constellation, so it's way up off of Sheraton, closer towards the Pisces. And the second object we have, before wrapping this phrasing up, is NGC 972. This is a spiral galaxy, but when you look at an image for this, it looks more like it's an irregular galaxy or a compact dwarf galaxy. I'm not quite sure if that's, well, or a compact galaxy. One of those two, excuse me. It's fainter than what you normally might want to go after, something about magnitude 11.3. It's still much closer to us, though, than NGC 772, 48 million light years compared to 113. Like many of the objects in the NGC catalog. This was cataloged by William Herschel in the 1780s, and it's actually closer toward Triangulum over here in the position. So as you can see, it's a very tiny galaxy overall. You'll probably just notice a greenish blade pluff, even at an 8-inch at 10 millimeters with a 10 millimeter eyepiece, making it probably a fairly difficult target to go after. But other objects that you might consider looking at just start getting worse and worse from there with much dimmer magnitudes. And here is kind of where I was saying this does not look like a spiral galaxy when you look at this. You can almost, maybe if you squint, kind of see some spiral structure like over here or over here, but it's also not quite sure if this galaxy is being seen edge on or face on, because that would kind of also determine it as well. But this does look like a little bit like a starburst galaxy. I'm not quite sure what Hubble filters are being used here, but with these thick, reddish clouds on the outer rim with what I would assume is star formation tells me that this is a starburst galaxy. Although what's triggering this massive amounts of star formation is kind of an interesting question, which I wasn't able to find a good answer to. And that's it. Any questions? Anything I want to go over again before we move on to Mars? Everyone just ready for Mars? Cool. Stephen, did you want me to drive?
Do you have my?
I do.
Okay. Yeah, that's fine. As long as I can see the screen.
Let me get this started. Can everyone see just fine?
All I can see right now is the Brady Bunch.
I think I might have.
Yeah, you stopped sharing.
Yeah. I hit the wrong button. There we go. Oh, which screen? Let's share. Not that one. I want this one.
There we go. There's Mars.
All right, there's Mars.
I don't have Mars. I still have your Aries slides. There we go.
I just blame your slow internet, Doug.
All right, so for those of you who are not delayed,
I got it now.
got it now, okay. Just be cautious that if we're having internet delays, it may be that I'm going to be a little bit ahead of you guys where the slides are. So I'm doing Mars, and this is not meant to be a comprehensive review of Mars. If we want to do that, it could go on for weeks. I'm sure there are astronomy classes out there at the university which go for a whole semester, and we're not going to do that. This is just kind of an overview. I wanted to, first of all, show a few pretty pictures, but my main goal is to talk about how to observe it. And the reason for that is that right now is the best time for the next 2 years to go look and observe Mars. It reaches opposition in the middle of the month, which means that it's opposite the sun and in the best position and near the point where it's closest to us to observe. I've been observing it for at least the last month since the skies cleared up after our pseudo monsoon here in Tucson, and it's definitely a good time to go out and look at it with a telescope. If you're into photographing it, that's great too, but I'm not going to talk about photography since this is AFSig and not a photography group. Next slide, please. So just some basic information about the planet itself. This isn't meant to be super accurate. I don't know how they come up with these very specific numbers, but within ballpark numbers, just to give an idea, its radius is about half of that of Earth's, Its surface area is about 0.28 Earths, which just about happens to be about as much surface area as all the land area on our planet. Not exact, but close to it. Its mass is about 10% of Earth's. Its actual tilt is almost the same as ours, it's 25.19 degrees. The temperature ranges quite a bit. It is a desert. The coldest temperatures are minus 143 degrees Celsius. The mean temperature is about minus 63 Celsius, which is typical Antarctic weather. Now this source cited 35 degrees max Celsius, which would be like 90 degrees. I'm really skeptical about that, but it does get up at least into the 50s and the 60s on the very hottest days in the tropics, but that's a very rare event. Typically, it's much colder than that. Its apparent magnitude is anything from minus 2.49 to 1.86. It's, I believe, above minus 2 magnitudes right now. It's pretty bright. Its angular diameter can be anything from 3.5 arc seconds to 25 arc seconds when it's in very close. And we'll talk a little bit more about why that's a big deal in a minute. You'll notice the big difference there. Surface pressure is 0.636 kilopascals, which is about a little bit less than 1% of an atmosphere. And its atmospheric composition is almost entirely carbon dioxide, a little bit of argon, a little bit of nitrogen, and very little bits of free oxygen and some other trace gases. Next slide, please. Okay, orbital statistics. What I want you to pay attention to with this is notice that aphelion, which is the farthest point, and the perihelion are quite different numbers, and that plays out in how we observe it quite a bit. And again, I'll go into some depth about why that's important a little bit later. Semi-major axis is 227 million kilometers. Its eccentricity is 0.09, which is actually fairly high, which means that its orbit is not really circular shaped. It's more shaped, I mean, all orbits are shaped in ellipses, but this one is more of a shape of an ellipse than Earth's orbit is. It's more oval shaped. Its period is 686 Earth days, or 668 sols, which are the length of time it takes for from noon to noon on Mars, roughly equivalent of their day. Its synodic period, which is, I believe, opposition to opposition, is 779 days on Earth, or 2.135 years, so a little bit over a year and a month for between oppositions. So next slide. So this is just to give you an idea of a rough physical approximation of Mars versus Earth. Mars is about half of our size and diameter, about 10% of our surface area, or sorry, about 20% of our surface area, and about 10% of our mass. As you can see, that Mars is quite a bit smaller than Earth. This is, I believe, an old Viking image on the right, and one of our Apollo images, I believe, on the left, showing this. Obviously, they are not that close together. This is a gross misrepresentation of the distance, but this is giving a rough idea of what the size looks like. Next slide. This is a map of some of the regions of Mars. It's not every region that's named, but it does go over the ones that are named, that are large features that can be seen from sort of Mars orbit. Mars, of course, has quite a few names. The names are taken from a wide different variety of sources, some of which were assigned for the dark and light features, the albedo features that once were documented from Earth. The ones I think I notice are things like Valles Marineris, which doesn't show it very well in that picture, but is along the close to the equator, Tharsis. And then if you're into observing Mars telescopically, you'll probably want to notice Syrtis Major. It's a very dark region right along the equator that's very visible from Earth, even through a small telescope. Meridiani is somewhat visible. And then Hellas, which we'll get to in just a second, is visible sort of a light patch inside the dark patches near the south. And those dark patches are important, and we'll talk about that in the observing section. And this gives some of the locations of some of the, a couple of the probes that have been landed. This is an older map as well. Okay, next picture. This is a topographic map of Mars, and as you can see, it looks a bit different when we do topography than when we do just photographic imagery. Notice that first of all, the dark patches don't necessarily line up with the topography. The dark patches are basically areas of dust that's darker than the surrounding areas, and we call those areas. We talk about albedo features, which is basically areas which are darker, reflect less light, and areas which are lighter and reflect more light. Those don't line up well with a lot of the features, with the exceptions of things like Hellas, which is a little bit lighter than the areas around it. Notice the huge difference in topography. Hellas, which is the blue circle down and towards the right, is the deepest point in Mars in terms of the lowest elevation. Is one of the largest impact features in the solar system. Not the largest, but one of the largest. And it's much deeper than the surrounding terrain. Up in the north, you have lowlands, which are a lower area, relatively smooth and relatively flat. And in the south, you have highlands, which are higher in altitude and deeply cratered. A couple features which stand out are Tharsis, which is over on your left, that red, brown, and white area. That tends to be the highest locations on Mars. Those are the very high altitude areas with the 3 Tharsis volcanoes. Olympus Mons is over to the left, right there. And then Velaeus Marineris is a area on I believe the eastern side of Mars, of Tharsis, which sort of cracked open and is a large tectonic feature that isn't well understood. Obviously, Mars does not have tectonic plates, but there are some tectonic features where things split, and there's been some movement of the crust, and that's one of the areas where that happened. Next slide. This is a comparison of Mars to all of the inner planets, the terrestrial planets plus Pluto. I don't know why they put Pluto in there, but it's what the picture has. Notice that Earth and Venus are quite a bit larger than Mars. Mars is bigger than Mercury, but not by all that much. It's a relatively small planet, not even for the terrestrials, where Earth and Venus are quite a bit larger than it. So that is an important thing to remember in terms of both the evolution and in terms of observing it. Next slide. This is a geologic map of Mars. The big things to notice are the large volcanic zones over on the left. That is Tharsis. There's a large amount of certainly not recent volcanism, but by Mars standards, younger volcanism. The brown areas, of course, are the old crustal highlands, which have quite a bit of impact basins on them, or not basins, but their impacts on them, plus the 2 basins of Hellas, and I'm drawing a blank on the other one, but they're in there. And then over on the right is the Elysium region, which is another volcanic plateau with some large volcanoes on them, where there's been some lava flows and the like. So Mars has a relatively varied topography. Up in the north, of course, is the lowlands with the sort of flat plains, not a whole lot of cratering compared to the southern highlands, which are pretty well bombarded. Okay, next slide. Next slide, please. Oh, there we go. I wanted to show a few pretty pictures of Mars since we're doing that. This, I believe, is either the northern or the southern regions close to the poles. You sometimes have these dark patches, which is where I believe carbon dioxide comes spilling out and pushes some dust up from beneath it. These are things that can be seen from orbit. I believe these are all from the camera on what is it? I'm drawing a blank on that.
HiRise camera.
HiRise, thank you. HiRise, thank you. HiRise camera that's currently in orbit is an older probe at this point, but it's still delivering some fantastic images of the surface. Next slide. Mars is a desert, in fact, a very deep desert. It's a very cold desert, but like all deserts, one of the features, it has a lot of their sand dunes. This is a dune field, not that different from what you might have in northern Africa or Arabia. Next slide. This is gives you an idea of what high-rise is capable of. This is the side of, I believe, a crater looking at towards the rim. High-rise can see features which are very small. I'm not exactly sure what the scale on this, but it's certainly a few hundred meters, I would guess. Looking at the side, you can see some of the outcrops of rock and the dust is with the talus slopes that are on the side of the crater. Just to give a sense of what this thing can deliver in terms of imagery. Next slide. This is an area where there's been obviously some erosion. There's interesting thing here is sort of the layering of the rocks. Mars does have a fair amount of sedimentary rock on it, and that's one of the features that our probes go after because it contains records of past environments. I don't know if this particular one is an interesting one, but it gives you an idea of the fact that Mars isn't just volcanic rock. It has some layers on it too, which is indicative of either lava flows that have happened at different times or potentially sedimentary layers, which are certainly interesting to observe. Next slide. Again, more dunes and outcrops of rock. Mars would be very different from Earth in that there's obviously no large living organisms there, including plants or animals, and so it's extremely stark and extremely barren. A lot of sand dunes, though, and dust that gets blown around by the wind. Next slide. This is another image of a crater. There's been a lot of interest in the crater rims. This image doesn't have them, but every once in a while there are little lines which appear within the slopes of the craters, and there's some debate about what causes that, whether it's caused by carbon dioxide, very cold carbon dioxide gas in a semi-liquid state sort of pouring down the sides, or whether it's caused by liquid water. This doesn't show a very good image of them, but the crater rims have been a lot of interest for the last several years by orbiting Mars probes, and it's still a mystery as to what causes that. Next slide. And this is another look at one of the crater rims. Notice on the right some of those odd darker features. I don't know if these are ones that are of a lot of interest, but certainly in different lights you can see some different features there. Mars obviously has a very old surface and a lot of craters. And sometimes the craters have some interesting features, but again, this is probably a crater that's about a mile across. And so you can see a lot of detail from the imagery. Next slide. Now some surface pictures. This, I believe, is Curiosity looking back towards Mount Sharp. Mars is covered in a lot of dust. We call this regolith. And of course, the tires of the rovers will go over that in order to get to their next target and gouge up a bit. You can get an idea of what this looks like. Mars has quite a few, there's obviously free rocks around along with the dust and the bedrock. But over to the right, upper right, you'll notice the slopes of Mount Sharp kind of rising, and off in the distance, the rim of the crater in which they're located. Next slide. This is an interesting image also, I believe, from Gale Crater that shows some of the layered sedimentary rocks. This is the kind of thing that the probe was sent to find in the first place because it contains a history of the planet mostly from earlier times. Mars has not been super geologically active for the last billion years or so, but earlier than that, there were certainly a lot of things that were going on. That's not really within the scope of this particular presentation. We've had a lot of presentations on Mars in the main lectures, so I don't want to get into that, but this is to give you an idea of what some of the rocks the probes are looking at, where you see the layers which indicate sedimentation. Next slide. This, I believe, is Spirit up in the Columbia Hills, looking back at, and this didn't render well, but you can see again some of the hills and areas, again, a lot of dust and barren rock. It looks very different from Earth in a lot of ways. The reason I like this picture is they didn't modify the lighting. A lot of the images you'll see coming back from Curiosity and even the old Spirit and Opportunity rovers, they modify the lighting to look like it would on Earth to make the minerals more easily observed. This one shows approximately what Mars would look like to an observer who is actually standing on it. Notice the very dusty brownish pink skies and the lower light levels than we have on Earth. It may be a little bit light enhanced. It might be a little bit darker in real life, but that gives a better idea than some of the other images we're looking at what Mars actually looks like. Next slide. This, I believe, is also Spirit. I could be wrong, but that's, again, looking at some of the features in there. A lot of lying rocks around and dust. I believe this is up in the Columbia Hills. Next slide. This is back in Gale Crater. Again, more of that exposed rock that they were looking for to explore. Gale Crater has, of course, Mount Sharp, which is a very large mountain in the middle of it. Curiosity's been scouting around on the lower flanks, looking at some of these exposed rock features. Next slide. This shows some of the buttes that are on the side of Mount Sharp. Again, you can see some of that layering that's been interesting to look at. These are mostly wind-blown features. So for the last couple billion years, almost all the erosion on Mars has been, as far as we can tell, probably all of it has been by wind features. There may have been some glaciation at different points, but a lot of what we're seeing is this areas which have been eroded by the wind and dust, but they kind of reveal some of those layers, which are certainly interesting. It's be kind of a cool thing to go see in real life. Certainly create some pretty postcards. Next slide. Again, these are some of the buttes that are in along Mount Sharp's lower flanks. It doesn't look all that different from some parts of Arizona and Utah, except of course there's no plants. Next slide. Again, some of that layered rock that shows the sedimentation, a lot of it in Gale Crater, which has made it such a great place to sort of explore Mars's history. As you go up the flanks of the mountain, you're going forward in history. So down at the bottom, here's the oldest rock that can be observed. And as you go higher up the flanks of the mountain, the rocks get younger and go to later ages in the history of the planet. Next slide. And this is Curiosity taking a self-portrait. You know it's Curiosity because it doesn't have any solar panels. And as you can see, it's getting pretty dusty, but it's taking that picture on the sides of Mount Sharp of itself. There's some cameras up in the head and a bunch of course, it's not nuclear powered in the conventional sense. It doesn't have a reactor, but it has some plutonium batteries on the back, which keep it powered regardless of what the sun levels is, which is very good for Mars because its dust storms tend to kill solar-powered probes, although not as quickly as everyone expected. So it's a pretty cool little probe. It's actually about the size of a small car, so it's not little, and it's been scouting around in Mount Sharp for several years now. Next slide. The real thing I wanted to do tonight is talk about observing Mars. So now that we're through the pretty pictures, I wanted to talk about some of the observational principles with Mars. Next slide, please. Mars is a hard target to observe, and it's a hard target to photograph. And I'm not going to go into the photography part, but I'm going to talk about the visual observations. It's got a bunch of complications to it. I do a lot of planetary observing, both imaging and observing visually. Mars is a real challenge. It's in some ways the most exciting planet to observe because there's so much you can see if you know what you're looking for, but it's also the trickiest of the planets, other than Uranus and Neptune, which obviously don't show much, they're so far away. But for the ones that are the major planets that we observe telescopically, Mars has a lot of challenges to it. The ones I'm going to talk about are the small size, the distance, is synodic cycle, which goes on a 2.5 or 2 year and about 1 month cycle. Problems that come up with the atmosphere, the altitude in our sky, which is a big feature that plays a role in between the hemispheres on Earth, differences in distances of oppositions, and then the albedo features, which have mostly very low contrast. Okay, next slide. So just to give some very cursory information on what the ancients did, for the Sumerians, it was Nergal. For Egypt, they understood the retrograde motions, which I'll talk about in just a minute. Babylon understood that it was the first culture to take really regular records of the planet. and it was able to sync up the synodic periods to Earth's years over a very long cycle. Greece included the model of the motion of Mars in his Almagest, including cycles and epicycles. Explaining the motions of Mars in the sky along with the other known planets at the time took up a huge amount of time and interest of ancient astronomers, partially because they were also astrologers, and astrologers need to know the positions of the planets and the background stars to work their hocus pocus. And so being able to predict the positions of the planets to a high degree of precision was an ancient obsession, which continues to this day. It's obviously important to know exactly where the planets are, but for different reasons now. Chinese records date as far back as the 4th century BCE, and it was known as the fire star. They tended to associate the planets more with the 5 elements rather than, or with their 5 elements rather than with gods or figures, and it was associated with the classical element of fire. Next slide. We'll talk a little bit about retrograde motion, and I wanted to explain just briefly what that means because it's occupied a lot of time for modern and ancient astronomers to try and explain what's going on. So at the beginning of the presentation, we talked about it's in retrograde and what that means. And astrologers get very excited about retrogrades and the various constellations. It's a bunch of, it's wonderful for them. But basically what it means is that for most of the time, Mars is very slowly moving eastward along the background stars. And what this diagram shows that as it closes in on opposition, that motion across the background star reverses and it heads west a little bit. And then for a few weeks it does that, and then it reverses motion, starts heading back east again. The reason it's doing that is that we are passing it up in its orbit. And so there's a weird little kind of geometric effect that we get as we pass it up. Now, for the ancients, didn't realize that that was what was going on, so they attributed all sorts of magical things to retrogrades. When Ptolemy tried to explain why the planets did this, his answer was, where everything's on spheres within spheres and causing things to move in odd directions. And it was one of the complications that some of the modern astronomers had to deal with as they dealt with the different models of the solar system. What's important to remember about Ptolemy is that he was made the conclusion that we were in a geocentric universe in which the Earth was at the center, and so his system had to be a little bit more complicated than some of the modern systems simply because he had to account for the fact that Earth was in the middle and not the sun. That's not to mean that the ancients hadn't proposed that the sun was at the center of the universe. Ptolemy simply decided that, and he wasn't Ptolemy originally. I think Aristotle was the one who was big on that, and everybody took from Aristotle that it was a geocentric universe. But that's just to give an idea of what retrograde motion means. Next slide. More recent observations, Copernicus used the retrograde motions of the planets to begin to justify his heliocentric theory. He, of course, published after he died and didn't remain in obscurity, but certainly was not accepted as a universal conclusion until a couple centuries later. Tycho made very careful measurements of the position of Mars. That was one of the planets he was focused most on. Again, a lot of Tycho's observations were both the star positions and the planets' positions relative to the stars. And Kepler included Mars in his theories of planetary motions, and he resolved most of the remaining issues for explaining planetary motion in the heliocentric model, which placed the sun at the center of the solar system rather than the Earth. And Galileo, as far as we know, was the first to observe it through a telescope and record it. So not that there were people who. Galileo did not invent the telescope. He took the design from a Dutch person who had been basically building spy glasses a couple years earlier and used it for astronomy. It's possible somebody else might have observed the planets first and never spoke about it, but Galileo is the first that we know about. Not likely, but possible. Next slide. In the 19th century telescopic observations, Schiaparelli was looking through a fairly large refractor. In the 19th century, the quality of the refractors had reached the point where you could fit them within a dome, and they became the standard observatory telescope of that particular period. And when he looked at it, he decided he saw little lines that he called canali. Well, canali just means channels in Italian. But then one of the most famous mix-ups, probably intentional in astronomy history, Lowell came along and decided they were really canals, and he built his observatory in Flagstaff in part to observe the canals of Mars. And the telescope is still built. His telescope's up there, is still built on Mars Hill, named in recognition of the fact that he was very interested in observing Mars as his sort of. He had several astronomical interests, but that was a big one. Next slide. This is the Canale Schiaparelli. I'm probably absolutely massacring his name. Saw it. He saw, of course, the dark features in the south, but he was seeing through a modestly large telescope, and there is a tendency in the human brain to see lines and shapes where there aren't really, and he decided there were, of course, these lines that were across the surface. Some of those dark features are still things that we see today very easily, even through probes that are sent there, but the lines, not so much. Next slide. And then Lowell took it a little bit further to canals. What you're seeing there is basically Lowell's somewhat, I don't want to say fanciful, but certainly exaggerated description of what the lines look like. His theory, of course, is the one that was popular at the time and sort of made its way into H.G. Wells' thinking of an ancient civilization bringing water from oceans into a dying desert and the like. And certainly his work inspired some of the science fiction that was out there for a long time. But he was directly believing that these were water channels created by Martians that brought water to agriculture closer to the equator. Obviously, no one has found those canals. They make for great science fiction reading, but they're not necessarily anything that shows up in reality. Next slide. So to talk about the first observer's challenge is the small size of Mars. So when we look at it through a telescope, Mars is not very big. It's only up to 23 arc minutes wide, which is arc seconds wide, which isn't very large at all. Jupiter is a bigger target in the sky. It's much further away, but it's also many times bigger than Mars. And so it makes an easier telescopic target than Mars does. As I said at the beginning, Mars is actually small even compared to the other terrestrial planets. So that's the first challenge you have to deal with when observing it. Next slide. The second challenge is the distance. The closest it's come in the last several tens of thousands of years was in August 2003, when it approached within 55,000 or 55 million kilometers of Earth. This year, its closest approach is, not closest, but opposition on October 13th is at 63 million kilometers, so there's a fair amount of distance. Its most distant is 4 times this when it's on the other end of the solar system. And because the fact that it's going around in its orbit, and it can be anywhere from directly opposite the sun to us to on the far side of the sun from us, its size changes quite a bit throughout its 2-year cycle, and it's only really observed for about 4 months out of every 25. We happen to be in one of those 4 or 5 months. This is an excellent time to go observe it, which is why I want to do the presentation night, because my big sell tonight is please go out and have a look at Mars in the next few days. It's going to be absolutely awesome. So go out and grab a telescope. Even a small telescope will show you the ice caps and some cool features. A bigger telescope will do better, but they have some drawbacks too. But go out and observe it. So the observer's distance is the distance. Next slide. So this is an idea of the fact that Mars changes size during its 2-year cycle. This is the current cycle taken between January and May, and they're shown at relative size. I don't know who created this as an amateur image. It's the C11 scope in Canberra. And it basically shows that on January 26th, you could barely see any features at all through an 11-inch scope. He's probably doing this with a modified webcam. And over the course of the following several months, going up through May, it got bigger and bigger and bigger. The reason I'm showing this is to show that the size changed. Mars is actually quite a bit bigger than that now. And this is the last one was taken in May, which is roughly 4 or 5 months ago. So it's gotten quite a bit bigger in the telescope since then. So just one challenge of when it's making its approach is the size difference. Next slide. Another observer's challenge is the difference in distances of opposition. So I said at the beginning of the presentation that Mars has a very elliptical orbit, which means that unlike Earth's orbit, which is almost a nice little circle, Mars has an orbit which is more oval shaped. And because of that, first of all, opposition is when the Mars is opposite to the sun in the sky and is therefore closest to us and brightest in our sky, and also has the biggest angular size, so it's the biggest in the telescope. But those distances are different from opposition to opposition. So sometimes the oppositions happen when Mars is close in near perihelion, and we call those the perihelial oppositions. The last one, the best one in our lifetimes was in August of 2003. We had one 2 years ago in August that was not quite as good, but still a pretty good one. The one this year is on October 13, 2020 is not a bad one. In fact, it's actually a good one for another reason that we'll go into, but it's about 36,000 or 36 million kilometers distant. Sorry, that's 7 miles at this time. But as you can see, as we go through the cycles going into the future, it's not going to be as good at opposition because it's going to be further out in its orbit when we get in close. And for that reason, this is a very good time to observe, because it is in fairly close to observe, and you'll get a big disk with a lot of details. Next slide. And this gives an idea of what Mars looks like at different sizes, depending on where it is in its orbit when it reaches opposition. Again, the 2003 one over on the right was one of the best that we'll ever see. It was the best that we will ever see in our lifetimes. And this gives the last cycle, again, the 2005 one, Mars was a little bit smaller to opposition. When we got to the opposite side, which is going backwards in time, but 1997, Mars was not very big in the telescope at opposition. Give another 3 or 4 cycles and Mars will be back in that position. So it won't be terribly easy to observe through the telescope at that point. So this is, again, a great opposition for that reason. But basically, different oppositions are different in terms of how big Mars appears in the sky and how bright. So you only get them every 20 years where they're really in close. Next slide, please. This is another image showing different sizes of what Mars looks like at opposition. This is the last cycle. 1995 was already pretty small. 23 was the best. And by 2007, when it came around again, it was already quite a bit smaller than it was in 2003. These are Hubble Space Telescope images, by the way. So this is what the best telescopes we have look like when they're looking at Mars. The reason we don't do this with probes in orbit is, first of all, you're not seeing them in opposition, they're in orbit, but also because the probes in orbit, unless they're in a very high orbit, don't see the whole planet. And none of ours are in that kind of orbit where they have a camera. So we use Hubble and Earth-based telescopes for the whole planet. Next slide. This is another observing challenge which sometimes comes up. Hasn't happened yet this year. But Mars has dust storms, and occasionally those dust storms turn global, and they tend to do that when Mars is in close to the sun, because you have more heating and more energy in the atmosphere, and that tends to stir up the dust. You get these windstorms which cause, well, it doesn't take a lot of wind to stir up dust on Mars, but they can cover the whole planet, and if that happens, basically the close approach is ruined. And I believe that happened in the last one in 2018. There was a dust storm that obscured a lot of the surface and made it very hard to observe in the latter part of the close approach. So get out with your telescopes now before that happens. Next slide. So another challenge is altitude. Mars reaches its closest oppositions in August, which means that opposition is always means that it's in the opposite position to the sun. Well, if the sun is way up in the sky in August, that means that the ecliptic is pretty far south. So the perihelic oppositions favor the southern hemisphere. This has always been one of the problems that we have when we look at really close oppositions, is that they are low in the south, and from the southern atmosphere, from the northern hemisphere. They're great if you want to go down and see them in Australia or Chile. But we have, because of they're low in the sky, they have a lot of obscuring atmosphere. This year, however, the opposition is happening in October, which means that the ecliptic, part of the ecliptic that is on, which is basically the path of the sun that the planets tend to follow, is fairly high this year. In fact, I was pointing my telescope not quite straight up, but pretty high in the sky a few nights ago when I was looking at it over the weekend, close to midnight. And that means there's much less atmosphere in the way. It's relative, so that's why this is a good year. It's relatively close, but it's also very high in the sky, which means we're seeing it through less atmosphere than we did a couple years ago. Next slide. The last challenge I want to talk about is the one that you have to go through at the eyepiece itself, which is the albedo features. So we're not seeing Tharsis, and we're not seeing volcanoes typically, and we're not seeing Valles Marineris through our little telescopes. They weren't really observed well until probes went to actually take pictures of the planet from orbit or in close flybys. What we see through the telescope is not that different from what Percival Lowell and Shapley-Aurelius saw a century ago. They're basically light features and dark features. This is one map of some of those dark features and light features. It doesn't have very good resolution. Sky and Telescope and Astronomy magazine both put out Mars albedo maps a couple months ago for their October editions. If you have those at home, go ahead and look at them. They show the features. I have one up here with me, but I won't show it to the camera. But that shows the named albedo features. Next slide. This is more of what I see when I look at Mars. It has them all named. Now, again, Mars is a fairly small target. They're not going to jump out at you quite like this. And in fact, the problem with them is, while the map showed a lot of contrast between the light parts and the dark parts, in reality, Mars does not have a lot of contrast. So the dark areas are not that much darker than the light areas. Now, if you know what you're doing, you can pull them out and they look pretty good. But just with the telescope pointed to the planet, even in a good opposition like it is now, it's going to be hard to see the contrast. So you need really good seeing in order to be able to enjoy the best of Mars and be able to pull out these low features. But if you want to, I was going to get to that. Yeah, the red and orange filters are a great feature for looking at the dark features. These are what some of the dark features look like. Syrtis Major jumps out at you as one thing that kind of jumps out because it is fairly dark and it is equatorially located, but I've seen Meroithrium pretty good, and you can sort of make out Hellas, even with an orange filter, is a little bit lighter than the areas around it. Some of it is again, it doesn't look quite like this, but you can make out these features if you're looking very closely and you have a nice steady sky where the image is really stable. Next slide. So here's what I use to observe. Some people are going to think I'm crazy for using an 80mm refractor. This is one of my favorite planetary scopes, as bizarre as that might seem, because an 80mm refractor theoretically wouldn't see very much. But I found with this one, the optics are good enough that you can put the magnification up fairly high. So I've got a fairly good eyepiece with a short focal length, which has a high magnification attached to a Barlow. And under steady skies, I can definitely make out the dark features and the light features pretty clearly. Now, they're not sharp like you get in a bigger telescope, but you can make out the patterns. As said, next slide. Oh, that's my other observing telescope that I use. This is an 8-inch Dob that I recently got. This is if you have one, is a great starter scope, but it's definitely a fun scope to use if you're just trying to do things visually, because it has a good aperture, is fairly portable, and it produces a fairly good image. I've seen some really impressive features on the planet through an 8-inch telescope. I don't have anything bigger than this that I use at home. Notice this on my balcony, which is not the best place on Earth to observe a telescope, a best place to observe from, but it takes away the risk of nosy neighbors, which I try to avoid in this time of COVID, so they can't get up there to observe. Normally I kind of do sidewalk astronomy with my neighbors and let them come and have a look, but I really don't want to deal with that at this point. But you can make out some fairly decent stuff from there. But this is a great scope for planetary stuff too. An 8-inch Schmidt is a good scope too for looking at the planets. And you can pick out a fair amount of features. If you have a bigger scope, use it. If you've got a 10-inch or 11-inch, by all means, aperture rules with planets. It's just a matter of hauling the thing around that can be really problematic. So again, use a larger telescope unless you've got a really good smaller scope to work with. A little store-bought refractor is not going to show much, but if you've got a good ED or an APO refractor, that can be a good scope to use as well, as long as it's steady skies and you're relatively confident in using it. Next slide. So this is the filters that we were talking about, and this is my sketchbook down at the bottom. So that's an example of what the planetary filters with. I've heard it said, and I think even Dean up in Star Arizona has said that the only filter you ever need is a variable polarizing filter. And for those of you guys who do filters, you know that's basically two little dark filters that you screw into each other, and you can rotate them to create different levels of light transmission. I actually disagree. I think that the old color planetary filters work really well. For Mars, the one you're going to focus on, and I use an orange filter rather than a red filter because I have smaller telescopes. With the smaller scopes, you want to use the lighter colored filters to do the same kinds of things that you would use the darker colored filters with the big scopes. The reason I do that is that the darker colored filters will tend to take out more light. All filters remove light, none of them add it. But the lighter color ones take out less, which is a smaller scope because they're not letting in that much light in the first place. So I use most of the sketches that you're going to see. I only showed a couple that are done through an orange filter because it heightens the contrast between the dark areas and the light areas, even in a small scope. You can use a blue filter and a little yellow filter, a green filter to look for some of the atmospheric stuff in the poles. I don't use it personally. I use those more for Jupiter and Saturn. But I find that if you want any filter for a Mars observation, use an orange if you're a small scope, or a red filter if you're using a scope that's 8 inches or bigger. That's generally the good dividing line with that. So those little, and these are obviously 1.25 filters that fit on the back of the eyepieces. So they're a nice little tool to have. They're probably the cheapest astronomy equipment you can buy, but they're a good thing to have for Mars observations. And next slide, please. And then I always recommend it, for those of you who've seen my planetary presentations before, always recommend that you get a sketchbook out and sketch this stuff. Yes, there's the Astronomical League, which loves you when you do that kind of thing for their kind of thing, but I'm not going to talk about that because I'm not a member. But I always take a sketchbook out anyway, because it really helps me focus on what the details look like. I take multiple sketches in part because as the night goes on, or I'll take a sketch right after I get started, because knowing that my optics have not equilibrated yet, and as it gets higher in the sky, it tends to get a little bit better to see. So I'll observe over maybe half an hour, 45 minutes. It ends up being roughly the same sketch, but I try to sketch approximately what I see. I don't bring out a map of Mars because I think it biases what you see too much. So I try and sketch out the best I can. Some of it is probably just wobbly seeing, so I'm making the assumption with these pictures that what I'm seeing, some of what I'm seeing is sort of like Schiaparelli and Lowell is probably not really there, but I try and be as honest as I can with the sketch. It certainly makes it more interesting. And of course, as the seeing varies, you're going to see slightly different things. So it's good to have kind of an attitude that what you're going to see is going to be a little bit different, not because the plan has changed, but because your image of it changes as you look at it each time. So I always get a sketchbook out. I have my little my artistic pencils and my eraser, and I use a little coin for the planet itself. Now it's exaggerated in size. It is not that big in the eyepiece. Certainly not to an 80 millimeter, but it gives you an idea of the rough images in that. So I have my sketching equipment, and that always helps me kind of focus on what it is I'm seeing and draw out the details. It's not meant to be a literal observation of every single bit of detail, but it kind of gives a sense of what I'm looking at. And it's a good tool to have. All right, next slide. This is just a rough idea of what some of the sketches look like. And I always record the time and the date and everything else up at the side. Mars rotates once every 24 hours. So if you wait for an hour or two, the scene on Mars actually changes because it's rotating around its axis, and you can see different features a couple hours later. And I've done that observation several times. You go out at 8 or 9 and then come back at about 1 o'clock in the morning, and you're seeing a very different scene than you saw a few hours earlier. Okay, and that's kind of what my sketch looks like, and just a bunch of little planetary sketches. Next slide, I think that's it.
Thank you very much.
Any questions? All right, very good. Thank you very much.
Can I ask a question?
Yeah.
So I had a couple of years ago when I was looking at Mars, I wasn't seeing much in the way of features, and I'm glad you talked about filters. I've got a polarizer. It's not a variable one. If I put that on my 12 millimeter, I've got an 8-inch Schmidt-Cassegrain. That's going to cut the light down quite a bit. Is that a good way to see, a better way to see features, or do I want more light?
It depends on who you talk to. What a variable polarizing filter will do is cut down on the glare. So if you've got an 8-inch telescope and you're pointing at a bright object, there's going to be a fair amount of glare. It can sometimes do a little bit to bring out some contrast. But I'm going to recommend that if you've got an 8-inch scope, at least consider getting one of the color planetary filters that's orange, because what that does is it subtracts light like any filter does, but it tends to bring out the contrast between the dark areas and the light areas a little bit. One thing I need to emphasize, though, is everything is dependent on seeing. So if your seeing is not very good, it doesn't matter what your telescope is capable of, meaning that if you've got, bad atmosphere, you can put all the filters on it you want, you're just going to see a blurry object in front of it, which is one of the reasons I like to play with my little 80 millimeters. It takes less time to equilibrate, and so it cools off faster, and so it doesn't have quite the bad seeing that an 8-inch or a 10-inch would have. Now, it still has bad seeing. That's not saying it's a magic telescope and doesn't have that, but it makes a little bit of adjustment. But what you're maybe dealing with is with the bigger scopes, you have to kind of wait for a while for them to cool off before you can get your optimum image. But I would recommend a color filter as well. At least try it out. I mean, the color filters are only like 25 bucks, or at least they used to be. They're not that expensive to buy if you're just putting it on a 1.25 inch thing. So if you're want to look at Mars, that would be my recommendation.
And it's smoky right now in Tucson.
Say again?
It's smoky right now.
Yeah, it's not ideal, but it's better than it was during the monsoon and the height of the summer.
The smoke has actually cleared up significantly since September. Me and a friend got a really decent photograph. Actually, let me just go ahead and pull that up real quick. Give me 1 second. Bring that back. So me and a friend were out at Tampa the week of, at the last outing in September. I think it was like the 18th or something. Come on, Chrome, please load. And
we're still seeing my sketches.
I know. I had my browser off on another page. just because it didn't want to distract people. So this is what we were able to pull off on my 8-inch using his little webcam. So this, for all this, and we had a lot of smoke up in the sky. I was doing some photography on M8 and M20, and those were some of the worst pictures of M8 and M20 I've ever taken. So this is actually we're really interested in getting back out because the sky is so much better now with so much less smoke. There's still some up there, but compared to September, it's significantly better. So I mean,
Nice image.
yeah. I mean, these are all.
Yeah. One thing to keep in mind about the planetary imaging and planetary astronomy is it doesn't need a terribly dark sky to be able to do it. These are very bright objects, even through the telescope. So I do almost all my planetary observing from my house, which is smack dab in the middle of Tucson. Anything else in astronomy, you need a dark sky for, but this is one you don't. You do need a clear sky, though, and you do need a stable sky. And sometimes the air coming off the city, especially when it's hot, is going to mess up your viewing a bit. But in terms of the light pollution, Mars right now is definitely standing out ahead of the light pollution. But if the sky is smoky or if it's hazy or if there's clouds in the sky, there's nothing you can do with it any more than any other object. But you're right, you got some very good images there of Mars. I'm now tempted to go take my 8 instrument out and do some photography tomorrow.
And this was we're really hoping to see, because this is so much closer to opposition. There's so much less smoke in the sky. So hopefully, if he actually comes out, we'll get like a image with double this quality. We hope.
Yeah. And one thing to keep in mind is that the photographed images look different from the visual images. So photography will bring out a lot that you can't necessarily see naked eye. On the other hand, if you have those instances of clarity in the visual, with a naked eye, or not a naked eye, with a telescope with your eye on it, you can see a lot of detail. But it's not going to look like that. It may, for an instant, kind of look almost like that, but it's not going to look quite like that. And plus, this is just a magnified image as well. It's going to be a little bit smaller. But so just be careful with it. When you look at a photograph, don't quite expect it to look just like that. It's going to look a little bit different in the scope than what the camera picks up. And you weren't taking this through any filters, were you?
Sorry. No, there are no filters on this. This
Okay.
was, I think, a 2-minute video stacked.
Okay.
Sorry, I got distracted with some stuff on my phone.
All right. All right, so my final message is go out and look at Mars. It's looking great right now. Go out tonight. All right.
Thanks very much, Stephen. Feel free to stick around, everyone, and chat for about till 8. After that, I'll close out the meeting.
Thanks.
All right, thanks, guys.
Great.